Hi everyone, in this video I'd like to talk more a lot about flow work and enthalpy. Enthalpy. Okay, let's say you have an energy balance on a system with mass flows going in and out, and you have heat and work interactions. And let's say these mass elements or these mass flows are fluids, and the control volume or your system is actually a fluid system. Now, when we have our energy balance, du dt of the system is equals to the work interactions, the rate of the heat interactions, the rate of heat interactions plus the rate of work interactions plus whatever energy is brought in by the mass minus the energy that is taken out by the mass flow rates out of the system. Okay, now when we talk about work, there are many kinds of work that can be done into the system. You basically put these into 2 or 3 categories. You have flow work, you have shaft work, maybe other kinds of work, such as electrical and so on. Now we won't be touching on this, we will mainly deal with shaft work and flow work. The shaft work is pretty straightforward. Let's say you have a turbine with steam coming in and steam going out. Turbine. And out of the turbine you have a shaft spinning. And you kind of get mechanical work out of this turbine. Now that is called shaft work. And maybe let's say you have a compressor. Let's say you have air going in and air going out. You want to compress this air, let's say using a syringe or something, or you have special pumps made for this kind of job. You're actually putting shaft work into the system. Alright? Now what is this flow work? Now when I started thermodynamics, and when I first heard this term, I couldn't actually really differentiate clearly between flow and shaft work. I was very confused, and I thought flow work has something to do with maybe the kinetic energy of the fluid, or something to do with the pressure. And you might start very confused, and maybe the reason you're watching this video is, well, you were as confused as I was when I just started. I made this video to kind of explain the concept of flow work to you. Let's say, I hope this makes it easier, let's say you have a cylinder or a measuring cylinder of some sort, or tower or column of some sort. Let's say you have water in there, alright, with a certain pressure P, and you want to actually get this amount of water into this cylinder. Now to get this in, to change its position from here into the cylinder, you actually need to push it in. you're not actually increasing its kinetic energy, but you're just trying to work against this pressure to push the water in. Now when you're done pushing in the water with this pressure P, and when you're done pushing it in, you would have actually exerted a force, and you have moved this distance delta x. Or in thermodynamics term, you have exerted a pressure moving across this volume. Now this is actually pushing in the liquid. Now this kind of work is actually referred to as flow work. Now you can actually do flow works by pushing mass into a system. You can also do flow work by pushing mass out of the system. Let's say again you have this cylinder out here, and in this vertical cylinder we have water again with a pressure P. Now the system here can actually get some of its water out, let's say from this little liquid bit out of the system, and it has to push against the cylinder to move it from here to here. Now this system has a pressure P, it's pushing against the surroundings with a pressure P2. Now how much work has it done? You have delta V, and you have a pressure P2 that you have to push it against. So the flow work done is P2 delta V. So just to get the liquid out from this cylinder to this area here, the system actually has to do flow work to get it from here to here. And now notice also that there's no kinetic energy change from here, which is stationary, to here, which is also stationary. I mean, in between you may have a movement of the liquid which relates to, and it constitutes the kinetic energy. But flow work doesn't really relate to kinetic energy. It relates to the energy needed to move the liquid from one place to another. So here you have to move it in, and here you're moving the liquid out. This is essentially what flow work is. Now let's say you have du dt of the system equals to q dot, and let's say we have all the different kinds of work here. We don't do this, we don't bother with the other kind of work. We have flow work, we have shaft work, we have the mass flows in and the mass flows out. And what does this little E hat represent? It is the per mass basis of the kinetic energy plus potential energy plus the internal energy. Alright, so this is what these E refers to. Now let's make it even clearer. By substituting this into our equation, and I want to differentiate between the flow work going in and flow work going out of the system. So let's say you have flow work in, and you have to minus the flow work out. So this should be a plus, and this, okay, let's do it this way. Half v squared plus gh plus u in minus the sum of mass out times the energy, kinetic energy, potential energy, and internal energy. Now let's say each stream has a unique flow work that's going in, and each stream has a unique flow work going out. And what is flow work equal to? Flow work of, let's say, a stream A equals to the pressure of stream A times the volume of stream A. And let's say you want to do it on a per unit mass basis. This will be equals to the pressure of A times the specific volume of A, called V hat. So we have du dt of the system equals to Q plus shaft work. Actually, I should have a shaft work in my earlier equation here. Now I need to include this into my energy of each stream. This one is the in, this one is out. Alright. And you know, every time we see this coming, we see this little U plus PV coming together a lot. And you know, we are usually just interested in the shaft work. We don't want to care about this flow work. So when we consider open systems where you have masses going out, masses coming in, you don't want to care about the flow work. So for the sake of maybe convenience, you want to group this term together as enthalpy. So let's rewrite our equation. Du dt of the system, the rate of accumulation of internal energy of the system, assuming the systems KE and PE are negligible in terms of change. You have the heat into the system, the shaft work into the system, plus other kinds of work, but we won't mention them here, plus this energy due to the streams coming in, plus the energy going out. Alright, and let's have a special case. We know we often see Q equals to delta H. Now, how did this come about? you actually have to assume a few things here. When you want to do Q equals to delta H. So let's write our energy balance equation again. Now this is a energy balance equation you can use for most systems. Let's say the streams, the kinetic energy of the streams, the change is about 0. You can neglect that. You can neglect potential energy changes. You can neglect the shaft work. Let's say it's just a pipe or a reactor vessel or something like that. You don't have to care about the shaft work. And let's say you have steady state. This implies the system's properties of any property doesn't change with time. So that will certainly include the internal energy of the system. Alright, now we can say this is 0 because of the steady state assumption. This is 0 because we assume, let's say we have no pumps or turbines or any kind of system that would add or take out shaft work. No compressors, nothing of that sort. We say the kinetic energy of the system hardly changes. Or rather, I just strike this off as 0. The potential energy changes are neglected. So we have 0 equals to the rate of heat flow in plus the mass and the enthalpy, the energy flows going in due to mass flows in, and the energy flow in, the energy flow out, energy flow out is due to mass flows out. And at the end you will get this equation. Now let's say you have one stream in and one stream out. So you will have M, because the streams in and streams out are the same mass flow rate. You have delta H hat H bar equals to Q. This is actually M H bar out minus H bar in equals to Q. M H bar hat H bar equals to Q dot. Therefore, delta H equals to Q dot. Now this is just a special case of this general energy balance. This is what you usually want to use to solve general problems. And if, let's say, you can assume special cases, you just cancel these terms off accordingly to make them equal to 0 so that your calculations can be simplified. I hope this video helps you understand what flow work and enthalpy is about and how to actually perform energy balances on open systems. Thanks for watching. Please subscribe, rate and comment.